A 2.6 billion parameter model is now running a multi-step agent on a phone without sending every token to a cloud model. But the number that matters is not the parameter count. It is where Liquid AI trained this model, inside real agent harnesses, including Hermes Agent and OpenClaw. Liquid calls the release LFM2.5-2.6B. The model card lists roughly 2.69 billion parameters, a 128,000 token context window, and a license designed for broad commercial use. Its job is not to replace the biggest coding or reasoning models. It is to make a smaller class of agent practical on hardware you already own. The official phone demo shows that idea in motion. A user asks for a multi-step travel plan. The agent reasons through the request, calls tools, compares options, and returns a structured answer. The model inference is local. External tools can still use networks and services, so this is not a claim that every part of the workflow is offline. The point is that the core planning loop does not need a giant hosted model for every turn. That changes the economics. If an agent runs hundreds of short tool calls a day, cloud tokens become a recurring meter. A compact local model moves that cost toward the device. It can also keep prompts, intermediate reasoning, and local context closer to the user. Privacy still depends on the tools the agent calls, but the model itself no longer has to be a remote service. Liquid did not train this as a chat model and hope tool use would appear. The release follows a staged post-training recipe. First, supervised examples teach formats and behaviors. Preference optimization shapes which answers are better. Agentic reinforcement learning then runs the model inside real environments, where success depends on completing tasks rather than sounding confident. That last step is the interesting one. Liquid names Hermes Agent and OpenClaw among the harnesses used in training. Those environments expose the model to long tool traces, failures, retries, browser actions, file operations, and verifiable end states. A model trained this way is not simply learning the syntax of a function call. It is learning when to call a tool, how to use the result, and when the task is actually finished. The official harness footage makes the training target concrete. You can see the model operate through requests, actions, intermediate state, and outputs. This is still a vendor demonstration, not an independent benchmark. But it is better evidence than a static score because it shows the kind of behavior the release is designed to produce. Liquid also reports strong instruction following and tool use results for the model size. On the published table, LFM2.5-2.6B is competitive with several larger compact models on structured instruction tests and tool sandbox. Liquid also reports an OpenClaw Browse Comp Plus result. Those numbers are useful for positioning, but they remain Liquid AI's evaluation. They do not prove that every workflow will be reliable. The same caution applies to speed. Liquid reports up to 220 tokens per second on an Apple M5 Max and 113 tokens per second on a Ryzen AI Max plus 395. Those are vendor hardware figures. Your result depends on quantization, context length, runtime, prompt shape, and memory bandwidth. So I ran one narrower check on a base M4 Mac. I loaded the official Q4_K_MGGUF in llama.cpp and exposed an OpenAI-compatible tool named lookup_travel_options. The prompt asked the model to call that tool with a route, a date, and a refundable-only boolean. On the captured generation, llama.cpp reported 44.31 tokens per second. The model chose the correct function and produced the right argument names. But the call was not strict JSON. It serialized the boolean as Python-style T true. A standards-compliant JSON parser rejects that value, so the tool loop did not complete without a repair layer. A wrapper could normalize it, but that would be our patch, not model compliance. This is one run, not a reliability benchmark. It shows both the capability and the brittleness of a small local agent. The model is available through GGUF, MLX, and other common inference paths. That makes it approachable for developers who already use llama.cpp on laptops or MLX on Apple Silicon. The model card also positions it for phones and edge hardware, where memory and power budgets matter as much as raw benchmark score. This is where LFM 2.5-2.6B makes sense. Use it for private, repetitive, tool-heavy work where the action space is bounded and results can be checked. Think local file organization, structured retrieval, device control, triage, form preparation, or small browser routines with explicit verification. Do not treat it as a tiny frontier model. Hard coding tasks, ambiguous planning, messy research, and high-stakes decisions still benefit from a stronger model and human review. Local does not mean correct, and agentic does not mean autonomous enough to skip guardrails. The release matters because it points to a different agent architecture. A large model can handle escalation, while a small local specialist handles routine execution near the user. Hermes Agent and OpenClaw are notable here because they are not just deployment targets. Liquid says they were part of the training environment itself. My verdict is simple. LFM 2.5-2.6B looks worth testing as a compact local agent specialist. The official demos show the intended workflow, and the published benchmarks support the positioning. But one limited M4 run also found a strict JSON failure before the tool could execute. The next question is not whether a 2.6 billion parameter model can attempt a tool call. It is how often it can finish a full workflow correctly. Subscribe for that test.